Good day, folks. Today we're going to continue with what we were focused on yesterday. Yesterday we worked on evaluating average rates of change, and that's something that's a skill that you've been working on since grade 9. Now, there's a reason we were reviewing that, and that's because the lesson today and much of this entire course will rely on those basics. Okay, today we're really setting the foundation for advanced functions. In particular, we're setting the foundations that you're going to rely on when you get into calculus. So here we're going to jump right in. We're going to practice a little bit of what we did yesterday. And we're going to try and take a new conclusion from those skills, because we're going about it in a very particular way. So we'll look at the first example here. The population of a city has been growing since 1950. The population in thousands and the time in years since 1950 are given in the table below here. And I want you to calculate the average rate of change in population for each of these 6 time intervals. I'm not going to go through these in detail with you. I'm just going to ask you to pause the video, try them out. Hopefully it will really get your brain thinking, and then I'll have you come back. So pause it right now, and then you can check your answers here. And let's get our handy dandy highlighter out. Where between 0 and 30 for values of t, then our average rate of change should equal 7/6,000 people per year. Don't forget your units there. Now 7/6, if you would like, it would make a lot of sense not to leave this as a fraction, although often in this course we will leave our answers as fractions. When we're working with an application problem, often we want a number that is more readily available to us. So you could absolutely write here, I believe it's about 1.17, let me see here, 7/6, yeah, 1.167. That equals approximately 1.166 on repeated. Next, from the interval from 10 years to 30 years since 1950. Our average rate of change should be calculated to be 3/2, or again, if you would rather, that's 1.5. And here I got a little bit lazy, 1,000 people per year. Even if we're getting lazy, we need to make sure our units are there, they're included. If I were being a little bit picky, what I should do, if I'm going to use this shortcut afterwards, then I should explain what it is. So 1,000 people per year is TPPY. Then you're just comparing what you calculated. If you found different answers than I worked through here, then I want you to double check your calculations. Okay, the thing that we're focused on here, we want to draw a conclusion. So we want to notice something about the average rate of change as we approach t equals 30 from the left and from the right. So that is, for these first 3 calculations that we did here, we're working from 0 to 30, from 10 to 30, and from 20 to 30. So I'm getting closer and closer. I'm calculating average rates of change closer and closer to t equals 30 from the left. Each of these first values are before 30. Okay, and then as we push forward, we calculate as well from the right. Again, we start with a larger interval and then it gets narrower and narrower. So first it's a 30-year interval between 30 and 60, then it's a 20-year interval between 30 and 50, then it's a 10-year interval between 30 and 20. Now what we do notice here is that our interval goes from, if we compare this to 0, then we begin and our average rate of change is a little bit over 1. And then our average rate of change increases a little bit. It gets up to 1.5, and then it keeps getting bigger up to 2. Okay, so that's when we're approaching from the left. It looks like it's getting closer and closer to 2. Now from the right here, we calculate first 9, and then it gets smaller to 6, and then it gets smaller yet to 4. So from the right, if we're approaching this interval here, this t equals 30 point, then we can see that our average rates of change are approaching 4,000 people per year. Okay, now and really that's what we should say is from the left, it approaches our average rate of change. I'm going to go very shorthand here, approaches 2,000 people per year. And from the right, our average rate of change approaches 4,000 people per year. We're not able to get any closer to t equals 30 because of the information we're given here. We don't have any information, any numbers between 20 and 30. We don't have any numbers between 30 and 40. So the smallest average rate of change we can calculate is between 20 and 30 years from the left and between 30 and 40 years from the right. Now what we want to do is we want to use, what's being plotted right here are the points, the data points right from the table. And then between those data points, we have what we call secant lines, right? So these secant lines, the slope of these secant lines represents our average rate of change between each pair of points. So in this case, our secant lines, we've not calculated them purely from t equals 30, right? We have some this year is calculated between 50 and 60. But hopefully we understand that what the secant lines at the very least represent. So if we consider these secant lines, the slopes of these secant lines, we can see that the slope begins as where t equals 0. Our slope begins very slowly, right? This is barely above a horizontal slope. If we look down here, and that makes sense if this slope looks to be something like 0.5. Right, and then the slope increases, it increases some more, it keeps right on going, and we notice here what we're working with is a pattern, right? It might not be a pattern that we fully understand yet, but hopefully we can see that the pattern is that it's increasing at the very least, right? So if we're using the slopes of these secants to predict a rate of change at t equals 30, one thing that we could do is we could take the secant line here and the secant line here, and we could see what's in the middle, right? So we can consider the secant line, or the slope of secant line, we'll call it secant line 1 and secant line 2. The slope of secant line 1 will equal the average rate of change that we calculated up here. So that's between 20 and 30 years. Between 20 and 30 years, our average rate of change was 2,000 people per year. So our slope would be 2. Our second slope, our second slope is between 30 and 40 years. That slope equals 4. So we could use these secants and we could average them out. We could take the mean. So that is we can predict at t equals 30. We can call it average rate, we can call it instantaneous, because that's really what we're instantaneous. That's what we're estimating here. Rate of change. That's what we're estimating. So we'll give it a nice squiggly bracket, is approximately equal to, and we'll say m1 plus m2 divided by 2. So we're taking the mean, right? And that is 4 plus 2 over 2. And I did run out of space, so I'm working sideways here. Not the best practice. That is approximately equal to 3. Okay, and this is again 3,000 people per year. So that is, although we did not calculate, none of these average rates of change brought us a value of 3,000 people per year. We can take the information that's there and use it to create an estimate, and in this case our estimate is 3,000 people per year, and this is relatively accurate. Now, could we have estimated this rate of change using only one secant line? Well, what we did is we just used two secant lines, right? We used, we used the secant lines 1 and 2, the green one and the yellow one here. If we want to estimate the average rate of change using only one secant line, then what we want to do is we want to create another secant line that includes 30, but it might not include the data point at 30. So the secant line that we want to take a look at here is from the year 20 to 40. Okay, if we can calculate the slope, we'll call it M3. If we can calculate this slope, this could also give us an estimation for our instantaneous rate of change, and we could do it by only working with one secant, and that will save us a little bit of time. Okay, so let's say we're trying that. If we're estimating our instantaneous rate of change, we'll call it our IROC. If we're estimating our instantaneous rate of change, then we could say, okay, well, that equals the population at 40, and that is 80,000 people. 80,000 people minus the population, and really I'll say, so that's P at 40 years minus the population at 20 years, all divided by 40 minus 20. That's our average rate of change here. And this leaves us with, bear with me here for a moment, so that's 80 minus 20 divided by 40 minus 20. Well, 40 minus 20 just equals 20. And that's approximately equal to 60 divided by 20, which again equals 3. So again, we would be working with 3,000 people per year. And this time we did that using only one secant line. It saved us a little bit of time. So in summary, we can use, sorry for the funny zooming here, folks. We can use the slopes of our secant lines, our average rates of change, to estimate, and that's key right here. What we're doing, it's only an estimation, to estimate the instantaneous rate of change. Sorry, folks, we'll see if I can get this under control. To estimate the instantaneous rate of change at a point. So we can use, we call it a preceding interval if it's the interval on the left side of a point. So that is our preceding interval that we used earlier, would have calculated earlier, would have been from 20 to 30 years. And that is this estimation that we came up with, where we said it was approaching 2,000 people per year from the left. Or we can use a following interval. So that's the interval following our point. That's our interval to the right side of our point. And in that, with that approach, we would have estimated 4,000 people per year. Again, not too far off of the 3,000 people per year that our estimates brought us to. Lastly, we can use a centered interval, and that has our point in the middle of an interval. That's what we tried in part C right here, and that gave us a little bit more accurate of an answer. So we will see. We're going to use the smallest option when we're calculating it. This is just a rule of thumb. In order to calculate it as effectively as we can, then we want to use the smallest interval as possible, because that's going to be what brings us closest to, in this case, t equals 30. Now that means that the smallest interval of our preceding, our following, or half of our centered interval. Okay, so a centered interval already brings us a little bit more accurate of an estimation, so we'll only consider half of that. Whichever is smallest, that's the interval we want to work forward with. All of these would have a similar value here, right? So that our preceding interval is equal to our following interval is equal to half of the centered interval in terms of what we'd be working with here. So they're all valid estimations. If this part confused you, don't worry too much about that. We can talk about it in class tomorrow. Next, we're going to work with the same situation, but this time they've given us a little bit more data. So our table from example 1, it now includes populations from different years, between 20 and 40 years, again, still after 1950. Here we want to estimate the instantaneous rate of change in our population at t equals 30 using each interval type. So we want to try using a preceding interval. Now, if we're using a preceding interval, then we're taking the average rate of change. So our estimate for our IROC, our instantaneous rate of change, is equal to the estimation. So it's approximately equal to our average rate of change. And it's this average rate of change that we're going to calculate. So in this case, if we're taking a preceding interval for t equals 30, then we're going to take the smallest interval that's available before t equals 30. So in this case, I want you to think about that for just 5-10 seconds. In this case, we're taking an interval using the data from the years 28, and 30. Okay, so we're evaluating that here. Our average rate of change should equal 40 minus 35.03 divided by 30 minus 28. We can throw that into our calculator right here. And I know we're using a calculator on this part of the lesson. If there is a question on an assessment for something like this, absolutely you would be allowed to use a calculator. So we're working with 40 minus 35.03. That brings us 4.97, all divided by 2. And that's 2.485. Okay, so 2.485. That's our estimation here. Again, 1,000 people per year. Now I want you to calculate the what our estimation would be for the instantaneous rate of change for our following interval, and our estimation for the instantaneous rate of change for the centered interval. Good, and after you do those, I'll say pause the video here as you calculate those, and then we can compare your answers to mine. I calculate here we're working with approximately 3.13, again, 1,000 people per year. And I should have gone with a different color here. Let's go with our blue. Our centered interval, our instantaneous rate of change is approximately, again, because it's an estimation, is approximately 2.81. That's what we should calculate for our centered interval. Again, 1,000 people per year. Don't forget your units, folks. Those are easy marks on an assessment. Now, we need to ask ourselves, which interval is the most accurate that we're using right here? Okay, so we need to compare, and how will these compare? We'll see. We need to compare these intervals, the interval sizes, if we're seeing which one is most accurate. And again, this is from this bit here. So our interval size, if we're looking at an interval size, we don't care about the population. All we care about is the time, right? So the interval size for a preceding interval is the number of years in between. Allow me to, we'll go orange, is the number of years in between the interval that we're taking. So that is 30 minus 28, that's 2 years. Okay, for a following interval, it's 32 minus 30, again, it's 2 years. For a centered interval, the interval is between 28 and 32. That's what we care about, and really it's only these pieces were what we took there. So here our centered interval size is 4 years, but when we're seeing which one is most accurate, then what we consider is only half of that centered interval, right? Because by the centered nature, it's already a little bit more accurate. And these are what we're actually working with here. That's delta t, right? That's the change in t, change in time. For this interval. Now, at this point, the intervals are, sorry, bear with me, folks. Good. So if we compare these intervals with the intervals that we calculated from example 1, the intervals that we were working on in example 1 had, when we estimated this average rate of change, we said it was approaching 2. So that was our preceding interval. And that had a delta t, that's right here, that had our delta t of 10 years. Okay, our following interval, again, had a delta t of 10 years. And when we took our centered interval, we were working with a delta t of 20 years. So we can say pretty definitively, we can say that the intervals from example 2 is more accurate because our delta t, our interval, is less, is smaller. In this case, we're comparing the 2-year interval. 2 years is smaller than the 10 years we were working with in example 1. Now, example 3 here, we have a whole new situation going on. So an equation that models the population of a city, again, it's a similar situation, but this time we have an equation, right? We no longer have a a table of values. So an equation is given here where t is the time in years and p as a function of t is a population in thousands. Here we want to determine the instantaneous rate of change at t equals 30. But now we have a little bit more at our disposal. So I want you to try out the best centered interval that you can come up with right here. And I want you to pause it here. I want you to come up with the best centered interval you can use. And just see if you're able to do it, because again, it's a little bit weird because we're working with an equation. If you were able to do it, great. If not, that's fine. We'll go over it right here. So here we're working, and we're just going to use one strategy, then we'll touch into another afterwards. So here we're using a centered interval. When we're working, we're going to choose, okay, so an instantaneous rate of change. Again, it's an estimation, so it's just approximate. It will be approximately equal to our population. Here we'll use 31 and 29, right? That's a nice centered interval. Our delta t is relatively small. P at 31 minus p at 29, all divided by 31 minus 29. Luckily, folks, as you can see here, luckily we're all masters of average rate of change by this point. Now, what we're doing is we need to calculate p at 31, right? So if we're calculating p at 31, that means it's 5 times 1.072, all to the power of 31. Oops, 31. And again, that's right from our equation right here. Minus p at 29. Okay, so minus 5 times 1.072, all to the power of 29, all divided by 31 minus 29. I know what 31 minus 29 is. That's 2. All right, I can throw that into my calculator, into my trusty, handy, dandy calculator, and I find that that equals approximately 2.801. And again, we're working in 1,000 people per year. Now, so this here, this instantaneous rate of change, you might notice that this had a delta t, and I'll go back to my orange here. This had a delta t of 2 years, right? Of 31 minus 29. Of 2 years, and since it's a centered interval, then this is more accurate than the 2 years we were working with in example 2. Okay, so this is the most accurate estimation we've come up with yet to this point through this note. Now, that's a good start. Can you think of a method to get even more accurate? You might already see it down here on the note. Even more accurate. Well, we can use a strategy that's called the difference quotient. So the difference quotient is an average rate of change, right? And that's all we're calculating. All throughout this note, we're just calculating average rates of change, and we're trying to use them strategically to estimate an instantaneous rate of change. This is just an average rate of change. So a difference quotient is an average rate of change with a very small delta. We'll call it delta x here, although in the applications above, we were working with t, with a very small delta x interval, and we call this interval h. This is used to estimate our average rate of change at a point x and f at x, and that's there's nothing new. We're just giving that a little bit of a formal definition. The smaller our value of h, the more accurate our estimate. Well, here we worked with two numbers that were very close to 30. They were only one away. Can we get even closer? Absolutely. We can make h very small. And what we're going to use in this course, what you could be using, is by very small, we mean h to equal plus or minus. We could go with 0.01 or we could go with 0.001. Okay, very, very small, that's our goal. The smaller it is, the more accurate it is. But there's no need to go to 0.00000000001. For most situations. We're not going to go the most accurate we possibly can go because there's no limit here, right? We could keep going smaller and smaller and smaller and smaller and smaller. We're not going to worry about that. Just 0.01 or 0.001 will be absolutely fine with us. So here is our equation. Again, this is an estimation for instantaneous rate of change, right? So f at x plus h minus f at x. Now, this is not a centered interval. If we take a close look at this, this is not a centered interval. What kind of an interval is it? Take a look, consider, think, look at your notes, we see we've worked with preceding, following, and centered intervals. We're working here with a following interval, right? Because it's x plus h, assuming h is positive. If h is negative, then we're working with a preceding interval, where h is very small. So we want to try it out. We'll throw this into our handy-dandy calculator when we work forward, and we'll see. So we're going to use a difference quotient, and here we're going to say where h equals, we'll use 0.001. All right, so now our instantaneous rate of change is approximately equal to p at 30 plus h, right, minus p at 30, all divided by h. Okay, so here we use h is the size of our interval. We previously, when we were working with in average rates of change, and we noticed down in our denominator we were always working with a delta t or more generally a delta x. That's what we're going to do here, but we're going to jump a little bit of a step forward. That's always going to equal h. So that equals approximately, that is p at 30.001 minus p at 30, all divided by h. And then we're putting these into our equation, right? So we're working with, that's approximately equal to 5 times 1.072, all to the power of 30.001. Thank goodness we have a calculator for this, minus 5 times 1.072 times, to the power of 30, all divided by, and I shouldn't have left that as h. I should have written that in as 0.001, all divided by 0.001. And we can throw that into our calculator. Try it out, please. Honestly, it is great practice to try it into your calculator, and then if it's not working, you can tell me in class tomorrow, and we can find out what's going on as we try them into your calculator. But we should find this equals 2.799 approximately there. Okay, so just a little bit less than 2.8. So here, now again, this is our most accurate that we've worked with so far with this situation, right? And we can say here that therefore at t equals 30, our population, if we put this into a nice concluding statement, our population is increasing at a rate of 2.799, and that's 1,000 people per year. 1,000 people per year, and obviously an easier way to write that is 2,799 people per year. People per year. Awesome. So I'm hoping that you can see the pattern that we've taken. We've strategically used all of these average rates of change. We've strategically used them with smaller and smaller intervals to get as accurate an estimation as we can. I know I went through every single thing in this note. I want you to just think about this. What is the best method for estimating instantaneous rate of change? I want you to think about that and bring that to class tomorrow. We'll have a bit of a discussion as we start off.